Encoders are other example of combinational circuit building blocks, and specifically they perform a function that is the opposite of that of a decoder. So let me show you an example. So in here I'm showing you a generic encoder, and a generic encoder will have 2 to the power n inputs and it will give me n outputs. But how would that pattern do? Well, in a general encoder, a binary encoder will have one of the inputs set to 1. For example, let's assume that this has like a bunch of inputs and that is set to 1 and the rest will be 0. Or let me call them asserted, because this assertion can be inverted. You can have like a bunch of 1s and just 1 0. Like one has to be different. Let me call it 1 hot. So the hot one in here has some sort of an index, and that index will be represented by the pattern of binary 1s and 0s at the output. And that's how an encoder works. So encoders are useful to reduce the number of bits. For example, you'll have 2 to the power n. Let's assume that n is 4, okay, for the sake of argument. So you have 16-bit input and you'll get 4-bit output. And of course, you can use a decoder to re-encrypt it, or like to interpret it again. What I'm trying to say in here is, like, if you have 16-bit input, you can represent the same 16-bit with only 4-bit. And this is useful for transmission. So you can transmit the signal, put a decoder on the other side, and you have the same exact signal. The decoder will have the 4 and will give me the 16 back, okay? So that's, I mean, encoders are useful and they have several applications. So let's go and try to implement a simple one. We're going to start by the 4 to 2 encoder, and as the truth table here shows you, you will have 4 inputs, okay, and we have a couple of outputs, and the output just tells me, like, for example, in here it's telling me that index 2 is hot, okay, and this is what index 2 in here. Index 2 is hot, and that's it. And that's how we do it, okay, or that's how the encoder actually works. So let's go to Vivado and just implement it using Verilog. So in here I created a new file, called it Encoder 4 to 2. So let's see how I implement it. First, as usual, we're gonna have to start by putting what my input and output are. I have an input and I'm gonna vectorize it. It's 3 to 1, 3 to 0, that's for the W, and I only have a couple of outputs. I'm gonna also vectorize them. And because I'm using behavioral modeling, this will be a register in here. Okay, so that's the register. All right, that's perfectly fine, good. And now, because I'm using behavioral, again, you can implement it with logic, but we're using behavioral modeling, so let's do always, and my sensitivity list will only have the the W. Of course, you can add an enable if you want to, but at this point, I mean, I'm just showing you how an encoder can work. Now we take a look at this circuit in here. Of course, this particular truth table I'm showing you here is incomplete. I'm only showing you the cases that actually matter to us. But of course, if I have 4, I should have like 2 to the power 4, which is 16 cases. I'm only showing you 4 cases. So of course I can go in and create a case statement or whatnot, or an if statement. So it's up to me to create it with an if else or a case statement. Let's start by implementing it with a case statement, which should implement it theoretically by a multiplexing network. So we're going to start by saying, okay, first I'm going to give y some sort of a default value, and you can create whatever default value you want. You can make it zeros, or frankly speaking, I'm going to do x's in here. And the reason why is because zeros is actually one of the valid cases. I just want to make sure, well, you can do that if you want to. You can give it zeros, but I'm just going to give it the x, which is don't know or don't care. And then I'm gonna say, okay, let's case test W, and then we say end case in here, and then we start. Well, if W can take one of 4 values, okay, or actually it can take one of 16 values because we have 4 bits. But what I really care about are these values, so I'm going to enumerate these values in here. So I'm going to say, well, the first case I care about is 0, 0, well, I'm going to tell it it's binary 0, 0, 0, 1, okay, and the next case I care about is 0, 0, 1, 0, okay, and then the next case in here is 0, 1, 0, 0, and then the last case that I care about is 1, 0, 0, 0. So at this point, there's actually no overlap between these in here, okay, so it is parallel case, but just to make sure that it's not going to match anything else, I'm just going to make sure that there's defaults, just so that I account for all the cases that are not shown in the truth table. And frankly speaking, I'm just going to go ahead and just make sure that y is just a bunch of x's. It's kind of like where we started with. Okay, you can put an x or a couple of x's, it will be expanded appropriately. Of course, now in here I can say, well, y should be 0, and then you can say y should be 1, and you can say here y should be 2, okay, and of course you can write all of these in binaries as well. If you prefer to write these in binary, you can just say it's 2-bit 1 0, it's the same exact meaning, okay, y equals 2 binary 1 1, okay. And we can test the functionality of this encoder by running its test bench. I went ahead and ran it in here, and this is what I got. I got the following. I got if W is 0, W is 1, W is 2, W is 3, okay? And we'll take a look at the truth table in here. So whenever W is 0, which is basically the inputs are all zeros, I don't have that case in here. It's a bunch of zeros, okay? So it should give me an X as the output, and that's exactly what I got. I got X's. Whenever I have the output to be, or the input W to be 1, which is this particular case in here, I should get Y to be 0, and that's good. Whenever I have this to be 2, I got the output 1. That's good. And then here, it's actually 3, which is not a valid case. 3 is actually 1 and 1 in here, which is not one of these, and it's outputted X exactly how expected. However, if I have 4, I'll have that in here. It will output the number, it should output the number... Well, 4 is this guy actually here, so it should output the number 2, and that's exactly how it's doing. 5 and 6 are not valid. 7 is not valid. 8 is valid, which is the last case in here, and should output a 3, and that's what you see. And you can see as well, it goes through 9, 10, 11, 12. It's just outputting X in here. That K is part of my test bench in here. If you actually go and read it, you'll see that I'm using that loop in here. I don't care about it. And what I see from here is my encoder is actually just working appropriately. Of course, I did not have to use case statement. I could have just used, I could have easily used an if-else statement. For example, I can just rewrite the whole functionality as the following. I can say if W equals 4-bit and a bunch of 0, 0, 0, for example. I can say that Y should be 2 binary 0, 0. I'm just writing that truth table in here. Else if, and then W equals 4-bit 0, 0. 1, 0. I believe that the first one has to be 1 in here. Okay, and then the next one should be that one in here. Y equals 2 binary 0, 1. Okay, and then else if, and then W equals 4 binary 0, 1, 0, 0. Okay, and Y should be 2 binary 1, 0. Okay, and here it's the last case, so I can technically include it with an else, but I will just say with an else if 1, 0, well, binary 1, 0, 0, 0, and then Y equals 2 binary 1, 1, and for the sake of completion, we'll say else Y equals 2 binary XX. And that should give me the same exact functionality, and you can run the test bench to double check. Okay, so taking a look at this diagram or truth table, you'll see that I have assumed that none of the cases, or not two cases, or not two inputs will actually be exactly 1 or asserted or hot. Okay, and if they were, we have outputted Y as don't care, and that's what's happening. Of course, when you take this don't care, it's only in simulation, or actually take it and you implement it in hardware, the hardware will actually figure out what it is and will give you some sort of a number or some sort of an output. We don't care about it because technically it doesn't happen. But it will happen in reality, and if it does happen, we need to deal with it. So encoders, generally speaking, are used in a priority fashion. So this is called a priority. This is called a binary encoder. A different one, it's called the priority encoder, and the priority encoder is different in that it tells me if there are 2 or more outputs that are asserted or hot, it will give me the index of that one with the highest priority. So let me explain. So in this example in here, I'm showing you a 42 priority encoder. The truth table looks a little bit similar, but it's actually really different. So here's how. It's telling me if Y3 is active or hot, I don't care what W2 or W3 or W2 or W1 or W0 are. I don't care what it is. I'm just going to tell you that that particular one is active because it has the highest priority. Similarly, if it was 0 and W2 is 1, I do not care what W0 and W1 are. Well, W2 is 1. That means I'm just going to give you the index 2 in here to tell you that that is the one with the highest priority that is active. So it's going to take a look at all the inputs that you have in here, and it will just give you the index of the one with the highest priority. And that's how a priority encoder works. And it's actually really important. I've seen applications, for example, if you have different sensors and one sensor is more important than the other and you want to generate some interrupt signal that you want to send, you can definitely do that. It will give you the index of that interrupt signal. But anyway, in here, I'm also adding another output in here. We call it Z, and the Z is just so that it's 1 as long as like there's some one of these W0, W1, W2, W3 has some sort of a hot. One of them is hot. If none of them is hot, I'm gonna just give you a 0, and I don't care about the index of the Y that appears. It's just a signal that tells me none of the inputs is hot. You shouldn't output anything, or if the output is out there, you just can ignore it. And that solves the issue if I have like don't cares on the hardware. All right, so let's move on to implementing this particular priority encoder, and then we'll move into generating a generic version of it. So in Vivado, now we're in a priority encoder 4x2. I already created it. Again, we have to figure out what the inputs and outputs are. They're very similar to the normal binary encoder. They're from 3 to 0 for W. And however, I'm just going to add another output in here. I'm going to call it Z, and I will have another output in here, and that will be a couple of bits. Okay, and I'm going to call it Y. All right, and from there I can just go on. So before I actually deal with the priority encoder functionality, I just want to deal with that Z in here, and taking a look at that truth table. It's telling me whenever all the inputs are actually zeros, this should be 0. And if you think about it, this is actually just an OR gate. So if one of the input is 1, or one or more of the input is 1, that means Z should be 1. So all I have to do is just take the OR of W0 or W1 or W2 or W3 and put it in Z. And of course, I can definitely just type this. However, Verilog comes with operators, and one of them is actually a reduction operator, and it's really useful in this particular case. What's a reduction operator? So let's see them. They're and, or, not or, X nor, okay, or not X or, okay. So what do they do? Well, and if you can see, it only takes one operand, okay. So, and as it turns out, the reduction operator, it's very useful in this case because I can just say assign, for example, Z equals OR of W. What is this reduction operator? It will take all the bits of W, no matter how long or how short they are. It will take all of their ORs, like W0, W1, W2, W3. It will just take all of their OR and it will just give me that number in here, or that bit, and it will just assign it to Z. And that's what we call a reduction operator. So it's really useful in here. And back to this truth table, you'll see that, yeah, if all of them are 0, Z should be 0. If one of them is 1, Z should be 1. And I just generated the output Z. Okay. So that's good. This is continuous assignment. You can definitely put it in an always statement if you choose to, but it's simple, so the choice is yours. All right, now we move on to the actual functionality of the priority encoder. Okay, so I'm now going to focus on the W1 and W0. So the way we do it is, again, I'm going to do it behaviorally, and I will do it. The input that I care about is actually W. Of course, if you have an enable, you're going to have to add it in here. And the way we're going to do it is actually, I'm going to do it a couple of ways, but it's a priority encoder. Priority is a keyword in here because it implies that I should probably use a priority routing network. That means I should probably use if-else statements. So let's start with that. First, I'm going to give Y some sort of a default value. I'm just going to give it an X's. You can give it 0. Well, you shouldn't give it zeros because 0 is a valid case. But anyway, you get the idea. So first, I'm going to say, okay, how do I implement this? Well, the one with the highest priority is this little guy in here. So I'm going to start by asking about it. I want its multiplexer to be at the very far right in there. So if W, and that is actually 3, is asserted, I'm going to do something, and that something is giving you the output Y equals 2 binary 1 1. Okay, I do not care what happens with the others because W3 is the highest priority. Okay, so that effectively ignores everything. If I'm doing else if and another else if and another else if, since all of them are within this if statement, I'm just going, technically I'm ignoring everything. So this is why you should not be using if and another if and another if and another if. Else if is a better case in here. All right, so we can test now W2, and we can definitely do the same exact thing. I can say Y equals 2 binary, I believe that's 1 0. Okay, and then else if, and then W1. If W1 is asserted, of course, if I write it in this particular order, and I'm assuming that I reach this guy in here, that tells me that W3 and W2 were both 0. That's why I reached in here. That's why I'm not testing for them. But technically, you can test for them if you want to. You can say, well, W2 should be 0, and W3 should be 0, and W1 should be 1. Okay, you can definitely do that. Let me do this case here. Okay, we can do that. Like, let me explain it to you what I meant with that. You can definitely say, well, not W3, and not W2, and W1. However, because I wrote it in the way I did, just so that I remove this here, so let me just do this reg. Because I wrote it with the way I wrote, that means I tested W3 and it was 0, and I tested W2 and it was 0. So if I reach here, this is implied because I wrote my if statement in this particular order. If I change the order a little bit, I might have to test it. So for sake of simplicity and code readability, I'm just gonna keep it in the simpler case. Here we do else if, and then at W0, that means my y should be 2 binary 0 0, and of course for sake of completion we do else and we say 2 binary xx, and that should implement that priority encoder. And you can check the RTL analysis or the RTL analysis to see this like cascade of sequence of multiplexes. But what I did is I wrote a test bench, so let's run it quickly just to see what it will give us. Hopefully it will work correctly. All right, so it's running in here and it's giving me the following. So I have a z here, and when the z is high, it's telling me that the output is valid. When the z is low, the output is not valid, which means all the input is 0. And you can see it's actually set to x. And again, the one here with the highest priority is actually with an index 0. The one here is with the highest priority is with the index 1. 3 is also the case. If you think about it with the truth table, 3 is actually W0 would be 1 and W1 would be 1. That means the highest priority is W1, and that's what I get in here, and the 2 here and the 3. So let's say 14, well, the one with the highest priority is definitely W3 because it's active. Okay, and I give you the index 3. So it is definitely working, and you can see it, I repeated it in here as well. All right, so that's perfectly fine. So that's how we do 42 encoder. Is there another way to do it? Can I use it with multiplexing network? Technically you could, so let's see that. Okay, so we're going to do that in here. I believe this is the priority encoder. So instead of this if statement, what I'm saying is, okay, let's use it with a case statement. So we're going to remove all of this in here, and we're going to say, okay, let's do this here. Case W, and then I'm going to say end of case or end case. All right. And then I'm going to say, well, it could be 4 binary 1. Well, what do I write in here though? Because I'm matching cases of W. Should I just say W000 and then 1 or it's like or 4 binary? You can definitely do this. Okay, but it's really tedious. Like I'm just saying you can do 1 and all the x's, you can account for all the x's. But if you think about it, I have 3 x's in here. That means I have 7 cases. Or actually 0 to 7, 8 cases actually I have. So I'll have to enumerate all of them. So can I just write 1 xxx? Let's see. And then 4 binary 0 1 xx. And then 4 binary 0 0 1 x. And then 4 binary 0 0 0 1. And then of course I'm going to say default, and in that particular case I'm just going to make sure that my y is x, and of course I can just do that. Frankly speaking, if you run this code, chances are it's not going to work, and I'm going to show you. Let's do this here. The fix is simple. I'll show you in a minute. Y equals 2 binary, let's say 1 0 in here, and then here y equals 2 binary 0 1, that's index 1, y equals 2 binary 0 0. Okay, so let's run this here. I'm gonna run the simulation. It should operate in the, it's the same module. I didn't change the inputs and outputs, so the functionality shouldn't change. However, you're gonna see it's not gonna work. I'm gonna get a bunch of x's, and this is common when you're writing test benches. Let's see. Everything I got is x except for the case when it's 0. That's the only case that is working. It's actually the first match in here. What's it telling me is it's just matching this guy in here, and that's about it. It's not matching anything else. Let me just see. It's actually 0. No. Which one is the 0? So it's only matching this, yes, because where is it? Here. Here. It's only matching this guy. That's the only one it's matching. The rest of them, this x, it's not understanding it. And as it turns out that this particular case doesn't understand what x is. It doesn't match it with anything. It actually matches it exactly the same. So it's looking for w to be 1 and a bunch of unknowns. It doesn't matter whether the unknown is 0 or 1. It has to be unknown. So if you want it to be treated as truly unknown, you're going to have to use something else, which we call a case x. A case x, in that case, it will treat an x as a 0 or 1 is a match. Okay, if you don't use that little x in here, it will be just a case. There's actually a couple of versions of the case. There's a case. Okay, we'll match it exactly as it says, 1xxx, okay? Or you can say case x, and it'll match the x as 0 or 1. And there's another one with a high impedance, which we're gonna do later. But for now, if you actually run it with a case x, and you just do this here and run the simulation, you'll see that, and it will actually interpret this as 0s and 1s. It basically will fill them out for you instead of just enumerating all of them. Okay, so we're gonna do this here, and it is currently working 0, 1, 2, 3, exactly like what we've seen before. And now I want to move into building a generic version of that priority encoder that can take any number of inputs and generate the appropriate number of outputs, and it will assert or tell me the patterns of ones and zeros for the one with the highest priority, or the input that is hot with the highest priority. So first, because it's a parameterized version, so I'm going to have to figure out the parameter. Okay, so the parameter in mind I have is n, and that's the number of bits. I'm going to just set it to default to 4. Okay, you can of course set it to 4, that will be 4 to 2, kind of like the one we built, but you can set it to any default you want. I have a couple of inputs. One of them will be n minus 1. This is because it's the number of inputs. Okay, w, that's basically my input, and of course I have an output z, and I have another output, and this time the output is actually y, and it will have the following indices. The least significant bit will be 0, the most significant bit will be based on the number of inputs. Because the number of inputs in here, let me explain it. So the number of inputs is 2 to the power n. That means the number of output in here will be c, or the log base 2. Okay, I'm just going to take the ceiling of the number n. Okay, and that's what we're going to do. So what does that mean? Well, 4, I wanted 2. All you have to do is just tell me, well, system function, the ceiling of the log base of n. And of course, I'm going to have to use -1 in here. So let's compute this. So 4, if you take the log base 2 of 4, it's actually going to be 2. 2 minus 1, or the ceiling of that will be also 2. So 2 minus 1 is 1. So 0 to 1, that will be 2. So I would have created a 4 to 2 encoder, or priority encoder. Like the same goes with a 5. If you start with a 5, you do this in here. So the log 2 of 5, it's going to be probably a 3, the ceiling. If you're taking the 3, minus 1 is 2, so I need a couple, which makes sense because if you have 5 inputs, and so forth. Alright, so now how do I do this? First, I'm going to do the z. We'll have the same functionality as before. All I have to do is just say, well, let's assign it. I'm going to use the reduction OR. Okay, and that's it. It will take all of the inputs of w, just OR them. If they're 0, it's just going to be 0. If one of them is 1, that means I have some sort of a valid input. Okay, that's good. And now here I will actually just write w, because that's it. I don't have anything else. And if I have an enable, I would have just written enable as well. We'll give y some sort of a default value. Okay, by default I'm gonna make it that. And now, well, it's a priority encoder, and I don't know how many. Well, I'm gonna use an if statement, but to make my life a little bit easier, I'm just gonna use it with a for loop. So all I'm gonna do is I'm gonna say for k equals 0 to k is less than n, k equals k plus 1. Okay, and then in here you can do begin and then end, and inside it I'm gonna test f w of k. Okay, then y equals k. I'm gonna explain what's happening. Of course, it doesn't like this. We're gonna have to fix this, make this as a reg, and before it, that k, I didn't define what type of variable it is. You have to define it as an integer. We have seen this for loops or for loop implemented before in a gen var, and you have to use a gen var here, but or there. But because I'm not using the generate and the end generate, I'm using it within an always statement. This for loop here is expecting an integer, so you have to write integer. It's not int, it's integer. Okay, and now fixes everything there. All right, so let's see what this is doing. And frankly speaking, because I only have one if statement, I technically do not need this. Okay, so here, what I'm doing here is I'm giving a default value. That's perfectly fine. And then I'm going to the inputs. Okay, each one of the inputs. So let me show you that on the diagram. So I'm gonna go to the first input in here. I'm gonna say, okay, WK, that's basically in the input, the very first input, is it asserted? If it is asserted, I will assert that number, or I'll give the output that particular number. If it's 0 asserted, I'm going to just put a bunch of zeros in here. Well, I'm going to go to the next one. If the next one is asserted, I don't care what happened before. I'm going to override that y, and I'm just going to implement it. I'm going to tell you y is asserted because one has the higher priority, and so forth. So I'm going to go all the way through. If I find one that is asserted, I don't care what happened before it. I'm just going to give that y will hold the latest value that is asserted. Okay, and that should implement the generic encoder, priority encoder, that is. Again, the C log in here is similar to the power. It's not implemented, it's a parameter. Okay, so it will take that number, we'll replace it in here, we'll calculate it, we'll do the 1 minus that, and then based on this, it will just replace every place with an n with that number 4. Okay, so I did write a test bench in here, and I created n, and I'm testing it with 6, for example. So let's do that in here. So we run the simulation. And here, so the simulation seems to work. This is my output. My output is either 1, 2, 3, 4, or 5, and 5 seems to be the longest because it contains many numbers, and you can just zoom in and just see it like if you prefer. Okay, so let's assume that my input here is 18, and technically, let me just show you that in binary. Okay, in binary, let me just zoom a little bit here. So in binary, that tells me there's a couple of 1s in here. What I care about is the index of this little guy here. It's 0, 1, 2, 3, 4. So I expect to see 4 at the output, and that's exactly what I got. It's the index 4. It's the one with the highest priority. The same goes with any of these numbers. For example, in here, you can see that this one is the one with the highest priority, and it's actually the most significant bit. It's 5, so I expect to see 5 to be active. K is part of some sort of a loop I'm using, and n is the parameter, so you can technically ignore them. And again, with the z, it's the same thing. Like you can see that z in here is actually low. That means all of the inputs are 0. Let's double check. All the inputs are 0. Z is low, and the output is x because it's not a valid input, or it's not a valid input. Yeah.